Earlier I told you that our topological sorting algorithm doesn't work if our graph has a cycle. Now let's see how we can detect a cycle in a directed graph. We need to maintain 3 sets of nodes. One set to keep track of all the nodes in our graph, one to store the nodes that we're currently visiting, and another one to store the nodes we have visited. The difference between the last 2 sets is that if we visit a node and all of its children, we put it in the visited set. But as long as we haven't visited all of the children of a node, we're going to keep it in the visiting set, okay? Now, in an interview, you may get asked to write an algorithm to detect a cycle in a graph using colors. That's just a trick question. Here we're calling the sets all, visiting, and visited. You could call them red, blue, and green. It doesn't matter. Now let's see how the algorithm works on a graph without a cycle. So we start off by adding all of our nodes to the first set. We pick any node in this set, it doesn't matter which node. So let's pick A. Now we start a depth-first search from this node. So we remove it from the first set and put it in the visiting set. Now we should explore the neighbors of A. A has 2 neighbors, B and C. Let's go to B, the order doesn't matter. So let's move B from the first set to the visiting set. Next we should explore the neighbors of B. So we move C from the first set to the visiting set. Now, C doesn't have any neighbors, so we're done visiting C, and we can move it from the visiting set to the visited set. The same is true for B, because B doesn't have any more neighbors to visit. So let's move it to the visited set as well. Now back to A. When we started our traversal from A, we went in the direction of B. Now we should go towards C, but we have already visited C, so we're not going to visit it again. We're done with A, and we can move it to the visited set as well. There is still one more node in our graph. Let's start a depth-first search on this node. Since this node doesn't have any neighbors, we add it to the visiting and then the visited set. Our algorithm is complete and we didn't find a cycle. Now let's change the direction of the edge from A to C and rerun our algorithm. Again, we start from A, we add it to the visiting set, then we look at its neighbor, so we add B to the visiting set too. Next, we add C to the visiting set. Now here's the interesting part. C has a neighbor, and that's the A. But we're not done visiting the A yet. We're still visiting it. As I told you earlier, we put a node in the visited set when we visit all of its children. So when we reach a node that is still being visited, that means there is a way back to that node via one of its children or neighbors. So our graph has a cycle. Now, if you want to print the nodes that are part of a cycle, we need to keep a map of each node to its parent. So we need a hash table here. Let's call it parents. We start again. In our parents hash table, we add A and null because we started our traversal from the A. We didn't come to A via another node. That's why we add null here. Now we go to B and add another entry to our hash table. Here we can see that we came to B via A. Next we go to C and add one more entry to our hash table. We found a cycle. Okay, now we use this hash table to construct the cycle. We know that the edge from C to A is definitely part of a cycle. Now, how did we get to C? Via B. But how did we get to B? Via A. And how did we get to A? Via no other nodes. So here's our cycle, A, B, C, A. Now I want you to implement this algorithm. So add a new method to our graph called hasCycle, and this method should return a Boolean. It shouldn't take you more than 15 to 20 minutes.